Dalton's law of partial pressures says that the total pressure exerted by a gaseous mixture is the sum of the partial pressures of each individual gaseous component of the mixture. So the total pressure, P sub T, is equal to the individual partial pressures of whatever gases compose that mixture. According to this law, each gas behaves independently. Now we know this isn't exactly the case, but this law assumes ideal gases. This law also tells us that the total pressure is dependent only on the total number of moles present, regardless what types of gas molecules are present. The mole fraction is the ratio of moles of one component of a gaseous mixture to the total number of moles of all components in the mixture. So to find the mole fraction of one gas, we take the number of moles of that gas, N sub 1, and divide the total number of moles of all the gases, N sub T, and that is equal to the mole fraction of that gas. Now combining these ideas, the mole fraction of one gas multiplied by the total pressure is equal to the partial pressure contributed by that gas. Now these calculations aren't that hard to do, but you must remember that the mole fraction is a ratio of moles and not grams. Let's look at a problem. If a mixture of gases contains 7.5 grams of hydrogen, 3.25 grams of oxygen, and 5.55 grams of nitrogen, what is the mole fraction of each of these gases? Remember that the mole fraction is a ratio of moles of one gas divided by the total number of moles of all the gases. Now I should point out that we're calculating mole fractions of gases, but this mole fraction concept works for anything. You don't have to just have gases. So in order to calculate the mole fraction of each of these gases in our mixture, we first need to convert the grams of each gas into moles of that gas. And we can go from grams to moles using the molar mass. This tells us that 7.5 grams of H2 is equal to 3.71 moles of H2. We're going to do the same for oxygen. Convert to moles using the molar mass of O2. That allows us to cancel units of grams and leaves us with units of moles, 0.102 moles of O2. And we'll do the same thing for nitrogen, using the molar mass of N2 and calculating that 5.55 grams of N2 are equal to 0.198 moles of N2. Now we've calculated the moles of each of the individual gases. So to calculate the total number of moles, we're going to add these numbers together. So N sub T is equal to 4.01. Now to calculate the mole fractions, we take the moles of each individual gas divided by the total number of moles to give us the mole fractions. So the mole fraction of H2 in this mixture is 0.925. The mole fraction of O2 is the number of moles of O2 divided by the total number of moles, which is equal to 0.0254. And the mole fraction of N2 is equal to the moles of N2 divided by the total number of moles, which is equal to 0.0494. Let's try another problem. A mixture of gases in a sealed container has a total pressure of 1.24 atmospheres and contains 0.953 moles of argon, 0.0426 moles of CO2, and 0.0175 moles of H2. What is the partial pressure of each of these gases? Remember that the partial pressure of each gas is equal to the mole fraction, which is the number of moles of that gas divided by the total number of moles, multiplied by the total pressure. So the total number of moles is equal to the moles of argon plus the moles of CO2 plus the moles of H2. So 0.953 plus 0.0426 plus 0.0175 to give us a total number of moles of 1.01 moles. Now to find the partial pressure, we take the mole fraction of that gas. So the mole fraction of argon is the number of moles of argon, 0.953, divided by the total number of moles, 1.01, multiplied by the total pressure, 1.24 atmospheres. So the partial pressure of argon in this mixture is 1.17 atmospheres. Repeating the same thing for CO2, The mole fraction of CO2 is the number of moles of CO2, 0.0426, divided by the total number of moles, 1.01, times the total pressure, which is equal to 0.0523 atmospheres, which is the partial pressure of CO2. And for H2, the mole fraction of H2, so the number of moles of H2, 0.0175 divided by the total number of moles, 1.01, multiplied by the total pressure, 1.24 atmospheres, which tells us that the partial pressure of H2 is 0.0215 atmospheres.